Welcome to our session on AP Statistics. Today, we are going to explore some of the most powerful tools in statistical inference. We have three main goals for today. First, we will define a sampling distribution. Second, we will learn how to simulate sampling distributions. And third, we will understand the Central Limit Theorem. By the end of this video, you will be able to describe sampling distributions using simulations and explain how the Central Limit Theorem allows us to predict the shape of these distributions. Let's dive in. To begin, we need to distinguish between a population and a sample. A sampling distribution is the distribution of values of a statistic for all possible samples of a given size from a population. Imagine we have a massive population, like every student in the country. It is usually impossible to measure everyone. Instead, we take a sample of, say, 50 students and calculate a statistic, like the average height. If we were to take every single possible group of 50 students and calculate their averages, the collection of all those averages would form the sampling distribution. Notice the distinction. A distribution of a sample describes the individuals in one group. A sampling distribution describes how the statistic itself varies across many groups. Our goal for this scene was to define a sampling distribution, and we've seen it's simply a map of all possible sample results. In the real world, it is almost impossible to collect every single possible sample. Instead, we use simulations to approximate the sampling distribution. Let's look at how this works. Imagine a jar full of beads where 40% are red. This is our known population parameter, p equals 0.40. We use a computer to simulate picking 20 beads over and over again. Each time, we record the proportion of red beads, which we call p-hat. As we record hundreds or thousands of these p-hat values, a pattern emerges. This resulting distribution of simulated statistics is our approximation of the true sampling distribution. By using this simulation, we can see how much we expect our sample results to vary just by chance. We have now met our objective of understanding how to simulate these distributions. A specialized type of simulation used frequently in experimental design is called a randomization distribution. It is used in experiments to show what happens by chance alone by reassigning response values to treatment groups. Suppose we have an experiment testing a new fertilizer on 10 plants. We find that the fertilized plants grew taller on average than the unfertilized ones. To see if this difference is significant, we simulate a world where the fertilizer does nothing. We take all 10 height measurements and randomly shuffle them into two groups over and over again. For each shuffle, we record the difference in means. This resulting distribution shows us what kind of differences are likely to happen just by random assignment. This is an approximation of the sampling distribution under the assumption that the treatment has no effect. We've now seen how reallocating values helps us understand experimental results. Now we arrive at one of the most important theorems in all of statistics, the Central Limit Theorem, or CLT. As sample size n increases, the sampling distribution of the sample mean x bar approaches a normal distribution. This is a remarkable property. It tells us that no matter what the paired population looks like, even if it is heavily skewed or very strange, the distribution of the sample means will eventually look like a bell curve if the sample size is large enough. Take a look at these three graphs. On top, our original population is not normal at all. But as we increase our sample size n, notice how the shape of the sampling distribution changes. By the time we reach a sample size of 30, the distribution is symmetric and bell-shaped. The larger the sample, the better this normal approximation becomes. This theorem is the reason we can use normal calculations for means, even when we don't know the shape of the population. We have now reached our goal of understanding the power of the CLT. Let's wrap up everything we have covered today to ensure you are ready to apply these concepts. First, we defined the sampling distribution as the distribution of a statistic for all possible samples of a fixed size. Remember, this is a distribution of sample results, not individuals. Second, we saw that we can approximate these distributions through simulation, either by repeatedly sampling from a known population or by randomly reassigning values in an experiment to create a randomization distribution. Finally, we explored the Central Limit Theorem. This essential rule guarantees that as our sample size grows, the sampling distribution of the mean will look more and more like a normal distribution, regardless of the population's original shape. With these tools, you are now equipped to describe how sample statistics behave and why the normal model is so prevalent in statistics. Great job today!